Well, greetings everybody. Here's a problem that I would really like to show you, and I'm taking it right off the assignment on MyMathLab. And here it is. A situation is described where we see an airplane off in the distance. It's flying right towards us. It will fly at a constant altitude, and it flies towards us in a way that it will fly directly over us. Okay? And then I name that the variable theta and the variable x are being described in the problem. All right, so I'll let you read that. I want to go straight to my picture because I think the picture tells you way more about it. So there's me. I see this plane off in the distance. It's flying towards me. It will pass directly over me. If I take my line of sight to the plane versus the line to the point right above me, that makes the angle theta. If I take the plane's distance horizontally towards me, meaning from here to here, that's x. This distance of my line of sight is not named in the problem and apparently isn't necessary. And then this side, it's got to be 300 feet because it said the plane's flying at constant altitude. All right, making this right triangle. Okay, so that's the situation as I read it. Now, before I get into it, here's what I like about this problem. What I like about this problem is I will do a calculation for the derivative and use tangents and secants and so on and get radians and degree, all this stuff that seems like somewhat complicated math. And I'll get these numbers that agree with my intuition. They agree with my experience, and I think that's important. You can just do math to practice it, but if you get a number and you think, yeah, I think that number is realistic, then it adds an entirely new dimension to it. I try to do calculus like that as much as I can. Okay, so here's why I think that when we do these calculations and we get these numbers, that they will seem realistic. I'll ask you to think about this situation. Imagine looking at this plane fly through the air when it's far away from you versus when it's close. Okay, as the plane moves a little bit through the air, this angle has to change, right? This angle tracks your vision, let's say. It goes from your line of sight to the plane. As the plane flies towards you, this angle collapses in a little bit. But what do you think is a bigger number? Let's imagine like this. Suppose this angle wiggles by a degree when the plane's further away, versus if this angle wiggles by a degree when it's closer to you, meaning more right above you. So imagine that this angle right here is gonna shift and move, wiggle just a little bit, you know, as it tracks the plane. Is the plane gonna move more when it's further away or right above you? Okay, I think, and probably you too, that if this angle was to wiggle by a degree when the plane's further away, that will make for much more movement in the plane, versus if this angle wiggles by a degree and the plane is right above you. I think movement in this angle by a small amount, let's say a degree, amounts to way more movement in the plane when it's further away versus when it's close. All right, now that's an intuition I have. I hope you have the same intuition, because to be honest, when I create this problem, it's entirely to appeal to that intuition of yours. Sure, we'll do the calculations, that's important too, but that really, I want you to have the same intuition as me and then see that the numbers bear that out, okay? All right, so now for the math, time for the math. We need to calculate the average and instantaneous rates of change. The average rate of change goes by the notation delta x over delta theta. The instantaneous rate of change, also called the derivative, goes by the notation dx over d theta. Okay, now to calculate the derivative especially, we need x to be a function of theta. In general, when you see this notation for the derivative, this notation is called Leibniz notation. We need this variable on top to be a function of the variable on the bottom. So if I'm going to find that derivative, I need x to be a function of theta. So let's start here. Is there even an equation that relates x and theta? Let's not even worry about the function. Is there an equation that relates x and theta? It would be tangent, because if you have a right triangle, tangent of the angle is the opposite side over the adjacent side. That's at least an equation that relates x and theta together. So we get this. And then it's not hard to solve for x and get another equation that puts x to be a function of theta. What do I mean by x being a function of theta? What does it mean to be a function? It means that I can start with theta, I can put theta in, and I'll get x out. That's how this formula is intended to be used. Plug the angle in there, do 300 times tangent theta, and the result you get is the x. Theta in, x out. One more thing. In engineering or sciences that deal with measurements, we need to be aware of units at all time. Units of measurement. Okay? The angle could be measured in radians or degrees, and x is a distance, and it will be measured in feet. Okay? All right, so let's now go through the problem. Now that I've got that function, I can do the calculations I need. So B and C are to find delta x over delta theta, and B if theta is 0 degrees and changes by 1/10 of a degree. Okay, so here's the formula for that. Delta x over delta theta, in this case, 300 tangent 0.1 degrees minus 300 tangent 0 degrees over 0.1 degrees minus 0 degrees. That's the change in x over the change in theta. This number on top is going to be what? Well, since it's the change in x, it's how much x changes, then it's going to be some change in distance in feet. So that top number is feet. This bottom number is degrees. 0.1 degrees minus 0 degrees. So you do your calculations there, you'll get 5.236 feet per degree. That's when the plane is close. I say that's when the plane is close because in B, the numbers we use were theta is 0 degrees and changes by 1/10 of a degree. 0 degrees, that would put it, 0 to 0.1 degrees, that'd put it nearly right on top of you, close. As opposed to part C, where it says, what is delta x over delta theta if theta is 60 degrees and changes by 1/10 of a degree? Well, that puts it much further out, right? If my line of sight to this plane makes that angle 60 degrees, I would say it's pretty far away, all right? As opposed to being right above me, which is what part B means. So part C, okay, theta is 60 degrees and changes by 1/10 of a degree. All right, under those conditions, there's delta x, the change in the distance of the plane in the air over the change in the angle of your line of sight. Those are the numbers. It's going to be a number in feet over another number in degrees. Calculate, divide, you'll get 21.007 feet per degree. That's when the plane's further away. Now, maybe, in the beginning I said, what is your intuition about this problem with respect to how the plane moves or appears to move when it's further away versus when it's close or right above you? Maybe you wouldn't have expected these exact numbers, but did you expect this to be a lot bigger than that? Okay, what does this number mean? It says, well, when the plane's right above me, for every degree shift in my line of sight, the plane moves a little more than 5 feet through the air. Versus when the plane's much further out, for every degree shift in my line of sight to the plane, it has to move a little more than 21 feet through the air. I would say that does agree with my intuition about this, okay? All right, why is that? Just imagine the triangle. If this angle was gonna wiggle a little bit by a degree, it would amount to way more movement out there. Versus if I was up here, the plane was right there, and this angle wiggled or shifted by a little bit, that would amount to much less movement, okay? You might also think of it like this. If I was shining a laser pointer out at a wall and my hand is not perfectly steady, that dot is going to jump around way more when I'm pointing further away versus when I'm pointing at a much closer spot. It'll just look like it's moving more. It's going to be more sensitive to the wiggles in this angle if it's out there versus out there. So that's why when the plane's further away, the distance it moves through the air is way more sensitive to any degree change in that angle. All right. So yeah, I didn't know I'd get these numbers, but when I thought about this situation, and hopefully you too, I did expect this one to be much bigger than that one. Okay, so that's the first objective with the problem, to get numbers that, even if we didn't know exactly what they're going to be, agreed with our intuition. I think that's important to do in calculus, because otherwise you're just doing math with no objective in mind. Okay. So next part was to calculate the derivatives or instantaneous rates of change. Because another question is, well, how do you think, like, if we can kind of agree about what the delta x over delta theta tells us, it tells me that if the angle shifts by a degree, the plane moves 5 feet through the air, for example. Or if my angle of my line of sight shifts by a degree, the plane has to move 21 feet through the air. Okay? How does that compare to the derivative? Well, the entire notion of the derivative is that all it is this, but when delta theta, or that delta on the bottom, when that change is very small. That's why the notations look so similar. And that's why we use this notation. Okay? dx over d theta is just delta x over delta theta, with the delta theta being extremely small. Okay? All right, so, well, here's what I would expect for the comparison between these two. Since, in fact, these were done, these average rates of change, the delta x over delta thetas, since they were done with the delta theta being fairly small, 1/10 of a degree in each case, then I would expect these derivatives to be close. Okay, let's see. So this first one in part D says, what is dx over d theta if theta is 60? All right, so we'll calculate that. Dx d theta, that would be the derivative of this function right here, 300 tangent theta. The derivative of tangent all by itself is secant squared. So dx over d theta is 300 secant squared. Okay. If we want dx over d theta when theta is 60, that'd be 300 times secant squared theta. All right. Doing that, just if you take secant of 60 degrees, square that, multiply by 300, you'll get 1200. Now here's something that might surprise you a little bit about derivatives when they are with respect to angles. Okay. The units in general, with the derivative as compared to the average rate of change, you'll have the same units. So like if dx over d theta had distance units over angular units, you'll still have that. So dx over d theta's units are going to be distance over angle. We were doing distances in feet here, but the default you get for the angular measurements out of the derivative, no matter what, are in radians. So this is going to be 1200 feet per radian. All right, that's just the way it's going to work. I know over here I intentionally can calculate those with the angular measurements in degrees, but the derivative just works out that it's going to give you feet per radian, or distance per radian. Now I would like to convert that to feet per degree, because I want to see how it compares over here. I'm expecting about this number. I'm expecting about 21.007 feet per degree, because they should be close. That's the nature of how this works. So I'd say, well, what is a radian? Do you ever think about what a radian is? I hope that you have, if you're in calculus. And I'd say, well, the simple answer to what a radian is, it's an angle, and it's about 57 degrees. There's a more complicated answer to that, but that's a simple enough, adequate answer. A radian's a 57-degree angle. Okay, it's true. A little more sophisticated answer is 1 radian is exactly 180 over pi degrees. Okay, now if that's true, that will allow me a way to convert. So I can do some dimensional analysis. 1 radian is 180 degrees over pi. That would cancel radians. That would give me feet on top, degrees on the bottom, and that would give me a number to compare over here. All right. So doing that, 1200 divided by 180 over pi gives me almost 21 feet per degree. That's what I was expecting, right? These are the actual changes. All right, this says if the angle changes by a degree, the plane's got to move 21 feet through the air. All right, those are like actual change in distances and angles. The derivative is just, it's like it's predicting that that's what it would be. Okay, so yeah, I didn't expect these to be exactly the same, but I did expect them to be close, and they are. Okay, so that's dx over d theta when theta is 60. Let's see how dx over d theta when theta is 0 compares to this number. All right, so I do the same calculation, 300 secant squared 0 degrees. I'm going to get a number in feet per radian. I get that even if I do this in degrees. Like if I put that degree angle there and I do secant squared with my calculator, well, I put my calculator in degrees, and you know it's going to give me 1200 or 300, right? That's my number, that's my answer, but my units will be feet per radian. Right? That answer is going to have those units attached to it unless you convert. Okay, so I get 300 feet per radian. I convert to feet per degree. I get 5.236 feet per degree. Okay, so then there they are exactly the same. If I had more decimal places, they would start to be different, but you know, whether they're exactly the same to 3 decimal places or not, I would expect them to be close, and they definitely are. Okay, so that's one, I think an important lesson in our intuition, that we get numbers to the degree to roughly how we'd expect that to work out. Okay, and 2, that the derivative does compare with the average rate of change, and that's why the notations are similar. Okay, let's see. I think that's everything I want to tell you about this. There are a few other problems in the assignment that play on similar themes to this, with comparisons between average and instantaneous rates of change. Beyond that, I hope it helped you understand something about our new notation for derivatives, rates of change, and all the concepts that relate them together.